This is a summary of all of Unit 7 about differential equations. This lesson goes over connecting differential equations and using them in context. Now, before, we did a lot with solving the differential equation, but there's also some other things that might be asked of you on the AP test. It might ask you to write an equation of a line tangent. It might ask you to use the tangent line to approximate a value. It could ask you to find the second derivative or anything about relative extrema concavity. This lesson kind of goes over these examples of all the other different types of questions they'll ask you. So if you look at example 1, it gives us the differential equation. So we're going to use a tangent line to approximate the value of 1.3. So we're going to write the equation in this form. Remember that your slope is actually equal to the derivative, and we do have a point here to plug in for x and y. So the slope is the derivative at the point. Let's substitute 1 for x and negative 4 for y. So we get that the slope of the tangent line is negative 1. And then we use this as the point. So again, y minus y1, which is negative 4. We have the slope, x minus 1. And if we simplify this by subtracting, well, I guess this is plus 4. So if we subtract 4, this is going to be negative x plus 1. But the plus 1 is going to be subtracted 4. So this is going to give you minus 3. So now we're going to substitute 1.3. And this gives me a value of negative 4.3. Okay, part B says find the second derivative. So the second derivative, we're going to use the chain rule. Not the chain rule, the quotient rule. So this is going to be f prime times g minus g prime times f all over g squared. So the derivative of what we call f is 4, and the derivative of g is going to be dy dx. So we're going to get 4 times g is y in this case, minus g prime is dy dx, and then times f, which is 4x, all over y squared. Now, notice that we have the first derivative again. Now, when you get to this case, we do have an equation for the first derivative here. So we're going to substitute 4x divided by y into this equation. So this is going to be 4y minus, and again, these will combine. So this will be 16x squared over y, all divided by y squared. And then if we get common denominators here, we will change 4y into 4y squared over y. And so on the numerator, we'll have 4y squared minus 16x squared over y squared. And then one final step, if I move this outside, my final answer will be 4y squared minus 16x squared over y cubed. And there is the second derivative. So we had to do a quotient rule and then resubstitute our first derivative back in and then simplify. Okay, so this is asking about relative extrema. Remember, the critical value is where the derivative is 0. And we need to see what happens when we plug in 1, 4. So let's sub 1, negative 4 into our derivative. So this equals negative 1. So this is not a critical value, and so it's neither. Because again, it would have to equal 0, and then you can look at maximum, minimum, relative extremas, and all of that. The first thing is that you need to have a critical value, which means the derivative needs to be 0, but the derivative is not 0 at 1, negative 4. Okay, so we're going to write another equation of a tangent line. So again, the slope is equal to the derivative at 1, 2. So we're going to plug in 1 for x and 2 for y, which gives me 8. So now, if we write the equation of the tangent line, we get this, and we can simplify if we want. So that's good. Now we're going to approximate 1.1 using the tangent line. So again, we're just going to sub in 1.1 in for x. So this is 0.1 times 8, which is 0.8 plus 2. So this will be 2.8. Okay, second derivative. So this is going to be a product rule. So let's consider this f and g. So the product rule is the derivative of the first times the second plus the first function times the derivative of the second. So f prime is 1, g prime is 3y squared, and then dy dx. So the derivative of the first is going to be 1 times the second plus x times g prime, which is going to be 3y squared dy dx. And just like the last time, we need to substitute our derivative back in because we have the first derivative here, and so we're going to substitute our original derivative back into the function. And if we want to clean this up, this will be y cubed plus 3x squared y to the 5th. Again, this combines with this to make x squared, and then we have y cubed and y squared. You add exponents when they're multiplied together, and so we get y to the 5th. All right, so kind of similar to what we did in the first couple of questions. Let's find our slope. So we're going to substitute x equals 1, y equals 2. So my slope is 0. And so the tangent line is just y equals 2. Okay, so again, doing the derivative, the second derivative. So the derivative of the top, so this is just going to be 1 times the bottom, which is just y. Subtract the derivative of the bottom, which is dy dx. Because again, the derivative of y is 1, but then dy dx, times the top, all divided by y squared. And then again, similar to the first two questions, we have to substitute our derivative back in. So this gives me y minus, okay, so this is going to be y minus, now these combine, think about it as this is over 1. And then if I wanted to keep going, I can write this as y squared over y. And then this numerator would switch to y squared minus x minus 1 squared over y. And then, again, if this numerator is on top, I could pull it outside. These two y's would combine. And there is my simplified answer. Now part C, so do we have a relative max or a min? So let's plug in 1 and 2. That does equal 0, so that is a critical value. So we need to figure out, there's two ways to figure out relative maxes or mins, and we can use the first derivative or the second derivative test. Now, we don't really know the first derivative. I mean, we have it here, but where does this switch from increasing to decreasing or positive to negative? Who knows? So we're going to use the second derivative test. And remember, if you are concave up, you have a relative minimum, and if you're concave down, you have a relative maximum. So let's do the second derivative test. Now we already have the second derivative from the previous part, and we're going to substitute 1, 2 into it. So this is going to be what, 4 over 8, which is 1/2, and that is bigger than 0. So we are concave up, which means we have a relative minimum at 1, 2. Remember, concave up means that you have a minimum. Concave down means you have a maximum. Concave up is when the second derivative is positive. Concave down would be if this was negative. So again, same questions. We're just going to do tangent lines. So we do need to substitute these values in for x and y. Or I guess this would be t, and this would be like this h. So my slope is -1. And then we're going to get y minus -1 equals -1. X minus -2. So this is going to be -x. So this will be +2, but we are distributing a -1, so it turns back negative. So this will be -2. And this will be +1, and then we're going to subtract it over. So my equation is going to be -x minus 3. And we want to approximate -1.9. So this will be positive 1.9 minus 3. So this will be -2.1. I can't add. This is supposed to be -1.1. Okay, find the second derivative. Okay, so derivative of the top is just going to be 1 times the bottom minus the derivative of the bottom, which is 2h dh dt, times the top all over h squared, which would be h to the 4th. So now we're going to substitute this back in for dh dt. So again, here we can cancel out an h. So this would be h squared minus 2 times t plus 1 squared over h, all divided by h to the 4th. And then again, similarly to what I did, I can change this to h cubed over h, and then combine them and get them down. But the final answer will be h cubed minus 2 t plus 1 squared over, and that will be the final answer. But if you can get here, you're good. So example 5, still doing tangents and slopes. So my slope is going to be equal to 1/6 times 120 minus r. And we know that we have at time 0, r is 50, so 0, 50. So 120 minus 50 is 70 over 6. I guess that's 35 over 3. So y minus 50. So there is my tangent line. Let's substitute 4 into it. We're going to get y minus 50 equals 35 over 3 times 4. And yeah, if you multiply this and if you multiply 35 times 4 divided by 3 and then add 50, you should get approximately 96.6 repeating. Okay, so let's find the second derivative. So my dr dt. Let's distribute. So that's going to be 20 minus 1/6 r. So the derivative here is 0, and then the derivative here is going to be r prime. And we're going to use the first derivative to plug it back into here. Or you can call this, instead of r prime, dr dt. And then we're going to substitute this back in. And again, that's just -1 over 36. And then 120 minus r. There is my second derivative. Part C, find a particular solution to the differential equation with the initial condition of r0 at 50. Okay, so multiply dt to each side. And then I'm going to divide by 120 minus r. I'm going to leave the 1/6 over here for the dt. And let's actually write the dr outside and leave this as a 1. So now that my variables are isolated, I do need to integrate each side. Right? This is going to be 1/6 t plus c. And this is going to be the left side. We're going to do a u substitution. The derivative of 120 is 0. The derivative of minus r is -1. dr dt. I'm sorry, not dr dt, just dr. And then so basically, we're going to get negative du is equal to dr. So this is the integral of 1 over u du. And again, I took the negative and I moved it outside. So this is equal to log of u. So negative log of u equals 1/6 t plus c. And then we do have to substitute back in 120 minus r equals 1/6 t plus c. And now we need to solve for c. We do have our point of 0.50, 0.50. So this is my constant, is negative log of 70. And from here, and again, what did I do? I just plugged c back in to my constant. Now what we're supposed to do here is solve for r. First off, I'm going to divide everything by -1 to turn that into a plus, that into a plus, and that into a minus. And then we're going to rewrite this into exponential form. We have e, and this is my exponent. It's over here to the right. This is the exponent of it, equals 120 minus r. And then if I subtract 120 and then divide by -1, I should get my final answer. And or a better way of thinking about it, add r to this side and then subtract that to this side. So we're going to get r equals 120 minus e log of 70 minus 1/6 t. And again, we could even simplify further if we wanted to, but we are good because this, we could separate this and this into two separate logs because they're subtracted. So this would be e to the log of 70 times e to the negative 1/6 t. And this cancels out the e with the log to 70. So actually the best answer is going to be 70 e to the negative 1/6. That is the best answer. That is a lot of heavy algebra though. So this next one is just writing tangent lines at different points. So again, my slope for the first one, for a, just plug in -1 and 4 for x and y. So it gives me 1/8. So we're going to get y minus y1, which is 4, equals your slope x minus -1, which would be +1. There you go. Part 2, the slope. Again, plug in -2 and -5 into your derivative. This is going to give me 0. So we have y minus -5. So that will be +5 equals the slope x plus 2. So if we simplify this, we're just going to get y equals -5. Part C, so again, my slope is going to be plugging in 2 and 0. This is undefined. So the tangent line is y equals 0 because a tangent line y equals 0, that's an undefined slope. Okay, so part D, describe all points in the xy plane other than y equals 0 in which the derivative is -1. So we have -1. Okay, solve this, multiply each side by 2y, and then solve for y by dividing by -2. And so that equation describes all points in the xy plane where the derivative is -1. You should mention too that y cannot be 0 and x cannot be, no, x doesn't have a restriction. E, same thing, so this is going to be 2. Solve, multiply 2y on each side, that's going to give you 4y equals x plus 2. Divide by 4, so we're going to get y equals 1/4 x plus 2 over 4, which is 1/2. And again, mention that y cannot be 0. All right, 7, almost finished. Consider this differential equation. Describe all points where the derivative is negative. So we want to know where this is less than 0. Now, we know that this will always be positive. So this is really all that affects. It's if the top is negative, then the whole equation will be negative. So any point where x is less than 2, the derivative is negative. Okay, now positive. Same question, just the opposite way. So we know that this will always be positive. So it depends on if the numerator is positive or negative. So we get every point that's greater than 2 is going to be positive. Okay, same thing here. Describe all points in the xy plane where the derivative is negative. So we have an x squared and 3 minus y is less than 0. This x will always be positive, right? So we want this to be negative. So we need to know where 3 minus y is less than 0. And that occurs when y is greater than 3.